So this one is a sampling question. It says, draw the structures of two stereoisomeric alkenes that would give 3-hexanol as the only major product of hydroboration, followed by treatment with alkaline H2O2. So they're saying these are the reagents, BH3, and then H2O2 and OH minus. So that tells us hydroboration, right? And so what do we know about hydroboration? So hydroboration, we know it is what kind of addition? We get what kind of products? Anti-Markovnikov, and we know it adds an H and OH, and we know the stereochemistry is syn addition, right? Hopefully. So we should just be able to ramble those off right at the top of our heads right away. And the question is, okay, what alkenes would actually make this product with hydroboration? So let's number the carbons first. So number the carbons, just 1, 2, 3, 4, 5, 6. So the question is, right, what starting material is going to give us the alcohol at carbon 3 only? There's two possible, we want two stereoisomeric alkenes. So where would we have our pi bonds? So if I drew out two possible things, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Where can we have the pi bond at to get the alcohol at 3 using hydroboration? Between 3 and 4, right? Now, how do I have two stereoisomeric alkenes? So this alkene, what kind of alkene do I have drawn here? Is this a cis or trans, E or Z? Trans, or E, right? But the other isomeric alkene I could use would be not a trans alkene, but the E alkene. Right? The other type of alkene I could make, the geometric isomer, will be the E. So I got to redraw. This won't work anymore. So I had drawn the trans. That's easy to draw, or the E. Can I draw the Z? So to draw the Z, I start like this. So that's carbon 3. That's carbon 4. 1, 2, 5, 6. So here is the E alkene, and here is the Z. And both of these will give only this product. All right, we'll give only this product. So good question. Why does it have to be between 3 and 4, not 2 and 3? Because if the alkene, if the pi bond was between 2 and 3, you could also get the OH at carbon 2. Right? Notice here, right? Is carbon 3 and 4, are they different? They're exactly the same. 3 and 4 are exactly the same, right? This molecule is symmetrical. If you had the pi bond between 1 and 2, right? If you had the pi bond between 1 and 2, are carbon 2 and 3 the same or different? They're different. But they're both would be secondary. And so I get an OH on carbon 2 sometimes. So if I only want the OH on carbon 3, the pi bond must be between 3 and 4. And so we'd have the E version and the Z version. This would give both an OH at 2 and an OH at 3. All right, another sampling question. This is has Cl2 and a solvent, a polar protic solvent. So this is a halohydrination. So it's not a halogenation. Right? Halogenation, we'd add 2 chlorines. In this case, because we have a polar protic solvent around, it's a halohydrination. So we know, right? What do we know about halohydrinations? We should know, right? It's Markovnikov products. We get a trans stereochemistry, right? So we should know also right at the bat that the solvent is going to end up on the more substituted carbon of the alkene. There's no rearrangements as well. So where would the more substituted carbon of the alkene be? Carbon 1 or carbon 2? Carbon 1. So we know that this should end up there, right? You should be able to almost draw this product without even drawing the mechanism right away. So let's draw the product right away even. So there I drew the product right away. So I said I knew the solvent was going to end up on the more substituted carbon. I knew it had to be trans to the chlorine that added. This is that halohydrin. You had a chlorine and a solvent. And they're trans to each other. So this is one enantiomer I have drawn. Hopefully maybe we'll get to draw the other one in a second. And we also, the other thing we make here is plus HCl in this case because we have the O from here and the other chlorine from here that ends up as HCl. Now, let's draw the mechanism. So what's the first step? The first step, what's my nucleophile? Pi bond. Reacts with the chlorine. The chlorine-chlorine bond breaks. A lone pair on the first chlorine comes back and bonds there in a syn fashion, making a chloronium ion, a three-membered ring, in a syn fashion. All right, so we have our syn addition. So I just showing the chlorine adding to the top face. The chlorine, there'd be another intermediate where the Cl, the chloronium ion, would be on the bottom face over here, but I'm just not drawing that out. So at this point, we have Cl plus, the three-membered ring, and we have Cl minus in the solution. Now, Cl minus is a better nucleophile than the solvent. But the problem is, what do you know about solvent? There's going to be a lot of it. So that first step is going to be, the next step is going to be that solvent reacting. And of course, the solvent's, because it's a Markovnikov, the solvent's going to go for the more substituted carbon. And this is going to be like an SN2 reaction, right? So you go for sigma star. Sigma star is 180 degrees away from this bond. So it'll be a trans, that's why we're going to get a trans product. Get that anti-addition. So the next thing we get, so that SN2 like, or SN2 reaction here, the biggest thing people will mess up is they'll want to lose this H or these carbons. Nothing happened to them. They're still there. They're still there. But people always want to lose them. Don't lose your carbons. Cl trans now. There's an H. And Cl minus is still floating around. And the last thing that happens, the chlorine takes that. And that would give us one of our enantiomers. But you draw the other enantiomer as well. Right? Where this is up and the chlorine is now down. That'd be the other version of this. The halohydrogenation. Halohydrination. Right, another sapling question, and this one's difficult because they're asking you to work backwards. So they're giving you the product and the reagents and saying, well, what did this come from? So the thing that might be difficult here is if you look at the reagents, which you should do first. You look at the reagents, you see Br2, and you see a polar aprotic solvent. You would think halogenation right away, right? That's what you should think. Br2Cl2 halogenation, polar aprotic solvent, right? So no halohydrination. But then you look at the product and you're like, whoa. There's one bromine and then all of a sudden there's an alcohol carbon bond. How'd you get a halohydrination happening? The only way this could happen is if it's an intramolecular reaction. Basically the idea being that this alcohol had to come from within the same molecule because it wasn't coming from the solvent because the solvent is polar and aprotic. So the solvent or the alcohol had to come from within the same molecule. So you take one step back, that would look like this. So you'd have a bromonium ion, right? If I number my carbons, 1, 2, 3, 4, 5, 6. And one step back from that, where do we make bromonium ions from? We can make those from alkenes, right? That's the title of the chapter, alkenes. So the starting material would be this. All right, again, Br2 makes you think halogenation. Polar aprotic solvent also makes you think halogenation. You look at the product and you don't see two bromines. That's confusing, but that means the alcohol part had to come from within the same molecule in an intramolecular sense. So you break that bond between 6 and 2. It came from a bromonium ion because Br2 always goes through a bromonium ion just like Cl2 does. And then where does a bromonium ion come from? It comes from an alkene. And it came from this alkene. So that's the way we work back. Yeah, another great comment. Right, balance these equations. The other byproduct here, the inorganic product, would be HBr. Right, that'd be the HBr would also be coming from here as well. So that's also in there. Absolutely. Good.